Oh, okay. Like this. Is that fine? Yeah, this is a different kind. Yeah. Okay. Okay. Okay, so I guess we are ready to start. I have your graded homework, so don't go away after the class. I will hand them out. I think there may be a few questions from homework, and we can talk about them briefly before we get to the next topic. But the main topic for today is going to be structures for computing FFT of real signals. So when the signal is real, then there are certain symmetry properties that we can exploit to simplify the structures, and that will help us reduce the computations. Okay, so are there questions about homework that we can talk about before we get to a new topic? Yeah, go ahead.
Question number 5. So it's asking to calculate the number of complex multiplications. So
Yeah.
does this include the entire block, like inside each small FFT and then between FFTs, and like, are you asking us to count the entire, how many?
Yeah, hold on, let me connect this one. Okay. Okay, so problem number 5. Right, yes, okay. Yeah, so what I am asking you here is to calculate a number of complex multiplications. So, okay, so what is the number of complex multiplications, roughly speaking? I mean, if you think about the log n stages, and one of the stages has no multiplications, depending on DIT or DIF. So either the first or the last has no multiplications, and the other one has n by 2. So really, I mean, it's n by 2 multiplied by log n minus 1. That's kind of okay. So rough estimate, number of complex multiplications is about n by 2 times log n minus 1. So it's about that. But we can, in DIT or DIF, we can definitely get a better estimate. So if we exclude multiplications by plus or minus 1 and plus or minus j, so that would be wn to the power 0 minus 1 would be wn to the power n by 2 and wn to the power n by 4, that's plus j. Well, actually that's minus j. So that's minus j. And then 3n by 4, which would be plus j. So that's minus 1. 3n by 4, which would be plus j. So if we exclude these things, then we can get a better estimate, slightly better estimate than that. So, let's take a look at what these look like. So I placed a number of papers and notes from previous semester written by TA, that times TA. So since I'm teaching something that is not in the book, so this so-called FFT notes draft, and there are mistakes, and I have not proofread this. This was written by TA. I have not even read it. I haven't read it, and TA was basically compiling my notes like the ones I'm writing down, and I was just browsing through before the class, and I found several mistakes. So, but you should be able to catch them. But it's better to have something than nothing. So this could still be a very good resource for you to read. And when it comes to real FFT, I'll start today with what was the way to compute real FFT before the 2009 paper. But let's take a look at, so I think this is a good paper in the sense that it has some very nice block diagrams. So if you look at the block diagrams in this paper, so let's go to one of the complex diagrams. Okay, so this may be a good one to look at. So let's take a look. It says here radix to DIF. So this is 64 point DIF. So in the first stage, how many multiplications do you see? So at the bottom, w to power 0 through w to power 31. So that's 32. That's what is n by 2. But if we want to get a better estimate of non-trivial complex multiplications, so we will exclude w to power 0 and then let's see here, w to power n by 4, which is minus j, and that would be w to power 16. So in this case, we simply exclude. So this is simply w to power 0 to w to power n by 2 minus 1, 64 by 2, 32 minus 1, 31. So w to power 16 is minus j. And so if I just exclude that, and w to power 0 is 1, okay, so the first stage, so there are 6 stages, right? 64, log 64 to base 2. So if you look at these, I think you are seeing my cursor, right? Yeah. So 1, 2, 3, 4. Okay, that's about it. And these ones are not there. So this is all minus j. So that fifth stage doesn't matter. No twiddle after the last stage. Okay. So so really log n minus 2, I guess. Yeah. Not log n minus 1. I could have taken log n minus 2 if I don't count the trivial multiplications by plus or minus j and plus or minus 1. So what is the number of complex multiplications here? That's n by 2 minus 2, n by 2 minus 2. First stage. Second stage, let's look at the bottom part. So now what we are seeing, instead of having n by 2 lumped together, it so happens that we have still n by 2, but they are in two different places. So that's in the bottom of the bottom half and bottom of the top half. So this is n by 4, n is 64, n by 4 is 16, and these are all the even powers. So 0, 2, 4, all the way up to 30. So that's the even powers, and if you go up, we see same thing. So that's the bottom of the top half, and w to power 0 to 30. So we still see n by 2, right? So n by 4 times 2, and you go to next twiddles, n by 8 times 4. So instead of 2 halves, we see 4 quarters. So this is quarter. 64, 64 by 8. So this is n by 8. N by 8 times 4 times. It repeats 4 times. 1, 2, that's 3, and that's 4. So 4 times n by 8 is still n by 2. But if we want to get rid of the trivial multiplications, so this is going to have 0 and 16, so that's 2. So this will be n by 4, n by 4 minus 2 here and 2 on the top, so minus 4. Okay, so I think I can now write down the multiplications. So this is really n by log n minus 2, so that's log n minus 2. Okay, so so a better approximation, this is approximate, if we exclude trivial multiplications by plus minus 1 and plus minus j, then number of multiplications, number of complex multiplications is equal to the first one is n by 2 minus 2. Okay, so the next one, there are two groups of n by 4, and in each group of n by 4 there are two trivial multiplications, so I can subtract them. In the next stage, 4 groups of n by 8, and in each group of n by 8 there are two trivial multiplications, all the way up to how many terms total? If n was so that's log n minus 2 terms, log n minus 2 terms. The reason we are not counting log n minus 1, that's just plus or minus j, and the last stage doesn't have any complex multiplications, it doesn't have any multiplications. Okay, so if you go through a little arithmetic, I think if you go through a little arithmetic, you can check this at home. I believe this should be n log n by 2 minus 3 n by 2 plus 2. Check at home. Okay, so this is a simple geometric series. Well, it is a constant, so n by 2, 2 times that is n by 2, 4 times that is n by 2, n by 2 multiplied by this number minus 2 taken outside a bracket, 1 plus 2 let's see, minus 2, minus 4, minus 8, yeah, minus the geometric series. Okay, so a little arithmetic, you should be able to, yeah, let's check at home before you do that. So what that problem then is asking you really is to use that number as the number of complex multiplications for each DIT or DIF structures. And then, so let's now go back to that homework problem. Okay, so okay, so I was asking you about, so if we are to compute 1024 point FFT, then the first one is just asking, so 2 to the power 5, okay, so let's see, did I specifically say what to use? I didn't say, okay, I didn't say, but you can assume DIT or DIF for the base structures. So just think about this as 32 times 32. So it's a composite FFT. Okay, so let's do this. Let's say that if n was 1024, so if n is 1024, then number of complex complex multiplications is going to be 1024 by 2 times log n minus 3 times 512 plus 2. So that's going to be 512 times 10 minus 512 times 3. Something like that. Yeah, something like that. Okay. Okay. So now, so the part A is asking if you use composite FFT. So you have a 32 point here, 32 point here. So what does that mean? So we have okay. So we have 32 point, and same here. 32 point FFTs, and then take the first term each and then the last term. Oh, this should really be at the bottom. Okay, so here. So that's, so basically, so the number of twiddles, what will be the number of twiddles here? So this is all 1. And this is 1, so this will be, any guess, any volunteers about how many twiddles in this composite FFT? (31 squared). Right, so there are, so first one doesn't have anything, and the remaining 31, the first ones are always constant 1, 31 squared, right? Anybody has a different answer, or anybody thinks it could be something else? So for the 3 times 5, it should be what? 3 minus 1 times 5 minus 1. 2 times 4, 8. So let's take a look what we have here. So first one doesn't have anything, so this is 2, and this is 4 and 4, 4 times 2. If I count from this side, 4 times 2, if I count from that side, that's 2 times 1, 2. Okay, this one doesn't count. 2 times 1, 2, 3, 4. Okay. So if we have 32 times 32, that's 32 minus 1 times 32 minus 1. And that's the number of multiplications in these interconnections, 961. Plus, there are 32 plus 32, 64, 32 point DSP. Okay, so then you substitute n equal to 32 here, multiply by 64 plus 31 squared will be your answer for part A. Yeah.
So for the interconnection, there are still multiplying negative j and negative 1.
Yeah,
So-
there could be, and yeah, you have to think about that. Yes, so there could be some number of those, and if you want to get a more precise estimate, yes, you have to exclude those. Yes, yeah, yeah. So you can find out how many j's and minus j's are here. Take a look at that. It's always instructive to look at that. But at least hopefully, is that making sense now? Okay. The next part I said 256 points. So 256 by 4. So that's really again a composite. So part B is 256 by 4. So if I didn't exclude trivial multiplications, so that would be number of complex multiplications in 4 of these plus number of complex multiplications in 256 of these plus the twiddles in the interconnection. So again, think about that, and there may be, try to count how many trivial, and it's always useful to take those out. And the part C is saying, well, this is the main difference between part A and part C is the first part stays the same, which are 32 points. The only difference is these 32 points are decomposed further using 8 point and 4 point. So in a way, think about that these 32 points are not DIT or DIF, and you can't use that formula, but rather think about these contain, each of these contains 4 8 point, and 8 4 point, and the interconnections. So that's why there is that bracket, and that means all of these 32 are replaced by this kind of thing. Is that making sense now? Okay. Bit involved, surely thought-provoking and a bit involved. But that's the kind of thing you think about when you are thinking about FFT structures. That's the kind of thing you think about. Okay. Any other questions on homework? Okay, so if not, let's continue to our main topic today of computing real FFT. So how do we compute a real FFT? A lot of the signals, well, I guess the dual problem is compute FFT of real signals and compute IFFT of conjugate symmetric coefficients. So these are dual problems, right? So if, for example, if I have a real signal, then it's for any real signal xn, xk is the conjugate of xn minus k. So for example, if n is equal to 16, then x0 is conjugate of what? X conjugate 16 minus 0, which is 16, and x16 is same as x0, right? 16, because it's periodic with period 16, which means that x0 is real. And you already know that x0 is simply the sum of all xn n equal to 0 to 15. And if all the xn are real, then x0 is real. Now what happens if n is equal to 8? Then x8 is equal to x conjugate 16 minus 8, which is also 8. And the only way that this can be conjugate of itself means that it must be real. So x8 must be real. So in general, if the signal xn is real, x0 and xn by 2 are always real. They have no imaginary component. Okay, so out of the n DFT coefficients, 2 of them are real. The remaining n minus 2, okay, I have assumed your n is even, so the remaining n minus 2 are going to be redundant. They're going to be redundant. That means in this particular example, if n was 16, these two are not redundant. Okay, so for example, x0 is sum of xn. What will be x8? Any volunteers? What will be x8 in terms of xn? Quickly, without thinking very much. So it will be summed over all n minus 1 to power xn, minus 1 to power n xn, x0 minus x1 plus x2 minus x3 plus x4 minus x5, like that. Okay, so so these are not redundant, but everything else is redundant. So out of the remaining, if it is 16 point FFT or 16 point DFT, there are 14 out of the 14, we need to only compute half of them. We need to compute only 7 because the other 7 are redundant. So x1 will be conjugate of x15, x2 will be conjugate of 14, 3 will be conjugate of 13, etc. So because of this, so the question is, how do we take advantage of this conjugate property so that we really don't compute? So the structures we have been studying until now are designed for complex signals. They are not optimized for the case when the signal is real. And a lot of the times, if you are monitoring a biomedical signal or computing some signal that is real, then using the complex FFT is not the best way because it's not optimized. So how many of you have come across a way to compute the FFT of real signal before the 2009 paper that we wrote? So computing the IFFT of conjugate symmetric coefficients is and the FFT is something that you come across in ADSL modems. How many of you have heard of the word ADSL? Asymmetric digital subscriber line, something like that. Is it digital or? I think so, yeah. ADSL. So the ADSL modems at the transmitter will compute the IFFT of the conjugate symmetric coefficients and then transmit that at the receiver. That will compute the FFT of the real signals. Okay, so how do those ADSL modems implement these IFFT of conjugate symmetric and the FFT of real signals? If you buy any modem, how do they have those chips implement those things? So, so let's say that we have, so the basic idea is to compute okay, so all those modems, what all those modems do is to implement an endpoint real FFT. So if it is a real signal of length n, it computes the n by 2 point complex FFT. And then from that, it obtains the endpoint FFT of the real signal. Okay. So what is the main idea? The main idea is, so if we have x0, let's say the signal xn is real, so this is the real signal. Okay, so x0 of 2, xn minus 1. Okay, so the very basic idea is let's collect the even samples and let's call them En, the even samples, which are nothing but x2n. So these are going to be x0, x2, up to xn minus 2. Okay, so those are the even samples, which are x2n, and the odd samples, let's call them On, the odd, which are x2n plus 1, and these are the samples x1, x3, up to xn minus 1. Okay, so okay, we are assuming n is power of 2 because that's usually how those modems are implemented. So we have the even samples and the odd samples. So what's the length of the even samples? N by 2. And the odd samples? N by 2. So I can say that using the same symmetry property. So xn was a real signal of length n. So xk satisfies conjugate symmetry, and that is xk is the conjugate of xn minus k. En and On are also real signals, but of length n by 2. This I can say Ek is going to be the conjugate of E conjugate n by 2 minus k, because Ek is of length n by 2, Ok is also O conjugate n by 2 minus k. So they also satisfy conjugate symmetry, but their lengths are n by 2. So instead of writing n minus k, just like the endpoint sequence xn, E and O, odd and even, are of length n by 2. So I can write them as Ek is equal to E conjugate n by 2 minus k, and Ok is O conjugate n by 2 minus k. Okay, any questions so far? Okay. So, okay, so that's so far so good. Okay, so how do I really, so if I'm computing the n by 2 point complex FFT, what is going to be the complex number input to the n by 2 point complex FFT? So what is going to be, this is of length n by 2, this is of length n by 2. Any thoughts about what might this input be? Any guesses? So this n by 2 point input is En plus j times On. So we have n by 2 point even samples, we have n by 2 point odd samples, which really I can then say as x2n plus j times x2n plus 1. Okay, those are the n by 2 point complex numbers. Okay, so so as a simple example, let's say that we had numbers like, so we have 8 point sequence like that. Then we input a plus jb, c plus jd, e plus jf, g plus e plus jf, g plus jh, and then compute 4 point complex FFT. And then from here do some post processing. To compute so if these DFTs are A, B, C, D, E, F, G, H in capital letters, then we will compute A, B, C, D, E. Well, okay, so A and E are real, B, C, D are conjugates of F, G, H. So we don't need to worry about those things. Okay, so so we'll do some post processing to compute x0 to xn by 2, x0 to xn by 2. Okay, so let me see your prior note. Okay, so we have looked at something like what we are talking about really. I mean, you know, if you look at when we tried to derive this DIT, FFT, you know, we had expressed xk in terms of the even DFT, that was the n by 2 point even DFT, gk, or in this case ek, and the n by 2 point odd DFTs, which was shown here. So we already derived the fact that xk is equal to, so I can write that down without further proof. I can write down xk is equal to ek, so that's the n by 2 point DFT of the even samples x2n plus w to the power k times OK. Okay, so we already know that, so that's we can make use of that. So xk, so by the way, xk is of length n by 2, but we don't need to compute all the redundant samples. So as long as we can compute n by 2, we are fine. Ek is of length what? So this is length n by 2. This is also length n by 2. But do I really need to compute n by 2 point DFT? Because of the symmetry of these, because of this is symmetric, Ek is E conjugate n by 2 minus k, OK is O conjugate n by 2 minus k. So it's really the n by 4 points. So all I need is n by 4 points of Ek and n by 4 points of OK. Okay, so let's call this one here as Zn is equal to that. So this is Zn and this is Zk. Okay, so we have this n by 2 point Zk. And then from that we will get to xk, but the first step is to get Ek and OK from this Zk. So that's the first step. How do we obtain Ek and OK from n by 2 point DFT Zk. I keep writing DFT because it's really the DFT coefficients. FFT is computing DFT, that's all. Okay, so how can I write down this? Okay, let me write this as Zk. This is Zk. So it's true that xk, but it would only be true for k equal to 0 to n by 2 minus 1. So Zk, so Zn is this. You take the DFT of both sides. Zk is the DFT of this plus z times the DFT of that is equal to that quantity. So then I can write down Zn by 2 minus k is equal to what will be this quantity. So this is going to be E n by 2 minus k plus w to power n by 2 minus k times O n by 2 minus k. Okay, so okay, w to the power n by 2 minus k, this is where there is some mistake, particularly here in the my not edited lecture notes that I posted. There are mistakes here in that note. I think that note wrote w to power minus k. I didn't read and correct those things. It was simply these kinds of notes copied by the TA, so I am just warning you that there are mistakes. So the first term is simply e to power j minus j pi, and that's just minus 1 times this minus minus becomes plus, minus minus becomes plus w, so that would be minus here, that's correct here. So that's minus w to power minus k, because w itself is e to the power negative power, and if I want positive power, that's minus k. So now here is what I want to do. If I want to take the conjugate, if I want to take the conjugate of this, so we take the conjugate of both sides. Conjugate of this is equal to conjugate of that plus the conjugate of this whole thing times the conjugate of odd. Okay. Okay, so so what is E conjugate n by 2 minus k? E conjugate n by 2 minus k is ek. O conjugate n by 2 minus k is ok. So this quantity then is equal to ek. Now what is conjugate of this quantity? Take conjugate on this side, conjugate on this side. Okay. What is the conjugate of this quantity? Any volunteers? Sorry?
Minus w to the power k.
Yes, exactly. Yes. Very good. Very good. So W is simply has a complex exponential. So its conjugate means just negate the coefficient. So EK, the minus sign stays because that's just a real quantity. And then W to power minus k conjugate is W to power plus k. Conjugate of minus k is plus k times O conjugate k. Now, why am I writing down all of these again? Because we are trying to get EK and OK from the n by 2 point complex FFT or DFT that we computed. N by 2 point complex FFT. Okay, so, and then we will use E and O to compute what we really need, which is xk. Okay, and I think, all right, okay, so now we have two equations, 1 and 2, and in your school, in our school or 6th, 7th grade, we have seen these kinds of things, right? So, I made a small mistake here. This is okay. O conjugate n by 2 minus k is okay. So is something plus something is something else, something minus something is something else. How do I get these things? Add and divide by 2, subtract and divide by 2. So if I add these two equations, what happens? This cancels out with that and I get 2 times that is equal to this plus that. And then EK is going to be half of this plus this. Okay. How do I get OK? Subtract, EK cancels out, minus becomes plus. So 2 times WK times OK is equal to this minus that. And OK is going to be, bring this to the other side, W to power minus K times a half times this minus that. Okay, so let me just write those two things. EK is equal to half of ZK plus Z conjugate n by 2 minus K. W to the power K, OK, is equal to half times ZK minus z conjugate n by 2 minus k. No, I made a small mistake here. No, this was, yeah, this. Okay, so I think what I am doing, so there is a small mistake I have made. Yeah. I could start all over again, but no, I made a small mistake. What I had written down was initially correct. So Gn is equal to En plus J times On. Okay, so what I wrote down was correct in terms of x. So this is really xk. So that one is correct for xk. But for zk, so this is correct for x. K, that is correct. So zk is simply equal to ek plus j times ok. Right, so it's that DFT plus j times that, and then all of that is correct. I didn't need that. I didn't need all of these things. Okay, so I don't need all of these things. So z conjugate is simply going to be, so the conjugate of j is going to be minus j. So, okay, let's just write down. Yeah, it's easy to make mistakes, and I shouldn't be doing that. Let's start from the beginning. So let me just start from the beginning. We will start from the beginning. Although I should say that everything is not lost, we will need those equations. So Zn is equal to En plus J times On. Zk is Ek plus Jok. Zn by 2 minus k is equal to En by 2 minus k plus Jon by 2 minus k. Take the conjugate of that, j becomes minus j, o conjugate. Then this is equal to Ek minus Jok. So Ek is equal to half of Zk plus Z conjugate n by 2 minus k. Ok is equal to 1 by 2j. J minus minus becomes plus j, 2j comes to the right hand side times zk plus z conjugate n by 2 minus k. Excuse me, minus. Okay, so those are simple ways to get E and O from the zk. So now we have E and O. So these are now available to us. Okay. So the last step is how can we get to xk? Okay. So now xk. So I think much of this still is okay. So this is x n by 2. So xk is equal to ek plus, that's correct. So w to power k times ok. So xk is equal to ek plus w to the power k ok for k equal to 0 to n by 4 minus 1. Okay. So that's xk, and what happens for k equal to n by 4 to n by 2? So for k equal to n by 4 to n by 2 minus 1, I can use the symmetry property of E and O. Okay, so we can write so what will be when k is greater than or equal to n by 4, how can we express that? In terms of a DFT coefficient that is between 0 to n by 4 minus 1. So if I use that property, Ek is equal to E conjugate n by 2 minus k. That should be more than enough, right? So if say k is n by 4 plus 1, this will be n by 2 minus n by 4 minus 1. And that will lie in the range 0 to n by 4 minus 1. So in fact, n by 4 plus 1 will exactly be the conjugate of that quantity, E of n by 4 minus 1. Okay, so we can say that for k equal to that, xk is equal to E conjugate n by, so Ek can be replaced by E conjugate n by 2 minus k plus w to the power k, and we need to express that as something so that quantity is greater than n by 4. Okay, so okay, so let me just go back to the work that we have done, and then so from this quantity what we showed here, w to power n by 2 minus k is minus w to power minus k. Okay. W to the power n by 2 minus k conjugate is equal to minus w to power k. So w to power k is equal to minus w to the power n by 2 minus k conjugate. Okay, so so the formula still is same, the formula still remains the same, but we replaced E k by E conjugate n by 2 minus k. W to the power k is minus w to power n by 2 minus k conjugate times OK is the same as O conjugate n by 2 minus k, which can then be written as E conjugate n by 2 minus k minus w to the power n by 2 minus k times O n by 2 minus k whole conjugate. Okay, so well, I mean, that's kind of what it really is. So that's how we obtain xk from 0 to n by 4, and then 0 to n by 4 minus 1, and then n by 4 to n by 2 minus 1. So if we call, there is a little more, if we call pk is equal to w to the power k ok, then xk can be written as ek plus pk, right? So ek plus pk. So I called w to power k ok as pk. So x ek plus that whole thing is now pk. K equal to 0 to n by 4 minus 1, and then is equal to E conjugate n by 2 minus k minus this whole thing is p n by 2 minus k, because we defined p of k is equal to this whole thing, and this is the conjugate of this whole thing, k replaced by n by 2 minus k. P conjugate n by 2 minus k, k equal to n by 4 to n by 2 minus 1. Okay, so that completes really what we are trying to accomplish. So, so this is how the post-processing that I was talking about. So if we have a n-point real signal, then take the even signal and the odd signal and separate them out and construct n by 2 point complex signal, so that becomes x2n plus jx2n plus 1, and that's now of length n by 2. Compute the length n by 2 DFT of that complex signal and call it as zk. So zk is of length n by 2, and from that length we get these things. We get ek and ok using that n by 2 point DFT by using these equations. Yeah, that's correct. Yeah. So so once we get ek and ok, and we multiply that by that w to power k, we call that pk, and then from e and p we can get xk. So that's that whole long process of post processing will eventually let us compute the n by 2 point real FFT, and the other points are conjugate symmetric, so we don't need to worry about that. Okay, so that's a little long process, but that's what the modems are doing. So they are computing the n point real FFT by n by 2 point complex FFT. Okay, so any questions? Okay, if not, so let's take a very quick look at the paper by Mario Garrido. He was my pre-doctoral visitor while he was doing his PhD in Madrid. He came to spend 3 months with me, and he was a student in that 5329 class, which I will be teaching next semester. And during those 3 months, he made some very simple observations that really eliminates the need for going through this roundabout process. So it may be a good idea to just try to quickly look at the very simple observation which we have talked about already, and then we'll see how that becomes the starting point for optimizing the FFT. So the basic idea is that the FFT structure after optimization is very much like the complex FFT, but we have simplified the structure to be very similar, but now the butterflies are real as opposed to complex. So okay. So if you look at this structure here, this is the 16-point DIF FFT. So we are computing the DFT coefficients in the decimated sequence 0, 8, 4, 12, etc. And the time domain samples are in place 0 to 15. Okay. So here is the very simple observation. So instead of what we were trying to, by the way, I should put that link. The process that I derived is the PhD thesis work of Sorensen. Sorensen's PhD thesis work at Rice University. I'll place that link for you with Sid Boras. And so that's that paper. All the things that I described so far, how to compute real FFT, that was, I believe, the 1987 paper, I believe. Okay, so instead of trying to say, okay, we will compute coefficients 0 to n by 2, and then not compute the remaining parts because they're conjugate symmetric. Here the argument is, let's try to throw out this computation of these redundant parts. Okay, so if you look at 12 is conjugate of 4, so that means I don't really need to compute that half a butterfly. This is a half a butterfly. This is 0, let's call this A and B. So this is A, B. By the way, these numbers that you see in this paper are the twiddles. You see these numbers 0, 1, 2, 3. This is W to power 0, W to power 1, W to power 2, W to power 3, etc. When you see these numbers 0, 4, etc., this W to power 4 is going to be minus J. Okay, so if this was A or okay, if this is A, right? So if this is A and this is minus J multiplied by that, okay, so you can see, if you backtrack, you can see that this will still be a real number, and when this is A and minus J times B, this is really not a butterfly. This is just thinking of that node as a concatenation of the real part and the imaginary part. So if this quantity was A, this is B, and A and B were here in hardware, they are still here A and B. We just recognize that, well, I can make that minus B. I can say, okay, and simply put that as A as the real part and minus B as the imaginary part. Okay, so we don't need this. Similarly, 2 is conjugate of 14, 10 is conjugate of 6. I need to throw this out, and I backtrack all the way as far as I can to the left, so that I throw away all the dummy computations that we don't need. So I don't need this butterfly. I don't need to compute that. I don't need to compute that. This half a butterflies are removed. This half a butterfly and this half a butterfly can be removed. We still need to retain these half butterfly. This is half a butterfly, bottom half gone. This is half a butterfly, bottom half gone. Now here, these are full complex butterflies. By the way, remember that 0 and 8 are real numbers. This is simply a conjugate number, as I explained, a minus jb. 2 and 10 are conjugate. These are fully fully complex, and that's their conjugate. These are also complex. 1 and 9 are conjugate of 16 minus 1, 15, 16 minus 9, 7. So these two are dummy. 5 and 13 are conjugates of 16 minus 5, 11, 16 minus 13, 3. And then we don't need these 4 things. So throw out all the things that we don't need. Keep going back. And if we keep going back all the way, we don't need these 2 complex butterflies. We do not need these 2 complex butterflies. And we don't need half of these 4 complex butterflies. We don't need, only retain the half a butterfly of the top and remove half a butterfly of the bottom. And what happens next? So what happens next is this goes straight, that's the real quantity. If you multiply this by minus 1, that becomes the imaginary quantity. And this complex butterfly, if this is A, this is a B, this is A plus JB, or A plus B, A minus B. I can think of this complex butterfly really as 2 butterflies, 2 real butterflies, A real plus B real, A real minus B real, A imaginary plus B imaginary, A imaginary minus B imaginary. And that I can then keep the real butterfly here, put the imaginary butterfly here, that picks up that space that became empty. These 2 complex butterflies are equivalent to 4 real butterflies, and we can expand them to 4. So this place that became empty, make these all real butterflies. And that half complex, if you expand, they become full real, one real. So in a way, what we have accomplished is we still maintain the n by 2 butterflies in each stage, but in each and every stage, we have n by 2 real butterflies and not n by 2 complex butterflies. So if we go through that, so what we threw out is gone here, these are gone, and that's what is part is thrown out. And then if we expand the half a butterfly to be 1 real butterfly, expand this complex to be 2 real and place the other real here. These 2 halves, half complex becomes 2 real butterflies, and then 2 complex becomes 2 real, 4 half become 4 real, 2 complex become 4 real. So every stage we have exactly n by 2 real butterflies, and it really looks exactly like the complex structure. These numbers are the twiddle factors. So again, we have now replaced all these half but complex to real. This is just concatenation, and then 1 complex became 2 real and 2 complex became 4 real. And so this is the FFT structure that is optimized for real signals without the need to compute an 8-point complex FFT and then go through a very complex post-processing step. Okay, I will kind of stop here because the next part of the paper goes into how to map that to a systolic array. In this particular paper, it's shown how to do that for 4 parallel systolic array, but we won't really get to that part in mapping, and that we will learn that part in the next semester's class for those of you who want to learn about how to map algorithm flow graphs to hardware architectures. Okay, so we'll continue next class with more about optimizing the FFT of real signals. Any questions before I stop today? But we'll spend more time. We will definitely spend more time talking about this next class. And that more or less will be your content for the first midterm exam. Okay.
When is the first midterm?
That is February 15th. February 15th, 2 weeks from Wednesday. So Wednesday, a week from that, you turn in homework 3, we grade it and give you back on 13th of February, and the exam is on 15th. Yeah. Okay, so don't go away again. I will, of course, have office hours here. If you want to ask more questions and your graded homework, please collect that before you leave. Quite a lot of time. Did it take a long time to type all this? Or you just like highlight? Yeah, so I have spoken like that before in the class. So I like writing. And maybe you can, if you like, you can share this with me because I know you are using laptop, right?